Hello everyone. In today's video we're going to be discussing the topic of benzene and aromaticity in general, taken from Chapter 15 of the McMurry Organic Chemistry textbook. So aromaticity is a word that historically comes from the smell of these molecules. Many of the molecules that we would call aromatic now based on structure are have a fragrance that is distinct. So while some of them don't smell particularly great, some of them have a sweet or somewhat attractive fragrance. A few examples are here: benzene, benzaldehyde, and toluene. Of note, the most common type of aromatic molecule that we'll talk about in organic chemistry is highlighted in blue here with this six-membered carbon ring with alternating single and double bonds. So 6 carbons in a ring with 6 pi electrons will make up our most common aromatic molecule, although we'll see that there are more ways to do this. Naming for these molecules will come up in just a little bit, but what we will find out is that many of them are based on the root name here, benzene, for the sort of standalone 6-membered carbon ring. And then we'll see some derivatives of that name. So benzene aldehyde would be shortened here to benzaldehyde. Some of them have common names like toluene, which is the common name here for methylbenzene. As we go forward, just briefly looking at the history, the word aromatic was described back in 1856. And importantly, the paper makes no mention of why that word was chosen. We're assuming it has to do with the smell. That's the common theory. But the molecule in question at the time was cuminic acid, which if you cook with cumin in the kitchen, popular in many different types of cuisine, the smell that you're getting is largely due to cuminic acid. Last little bit of history here. August Kekulé proposed the first structure of benzene, showing this alternating single and double bonds based on a number of things. Published here in 1872, these are some of the original drawings, and so you can see that he did have this sense of alternating single and double bonds. What I particularly like about this are just these pictures I lifted from Wikipedia showing that the German government honored him with a couple of different stamps over the years. As we move forward, modern usage here, the word aromatic now refers to a class of compounds that have a particular electronic structure. Again, most commonly we'll be talking about using this benzene ring. So we see benzene here as a parent molecule. A couple other examples we saw in a previous slide. We'll also see many biologic molecules. This is a typical steroid structure containing that aromatic ring in one position, as well as many pharmaceuticals include aromatic motifs. And so we have here Lipitor, a classic, very popular cholesterol-lowering drug. Where do these come from? Well, the answer is, as it is for many organic compounds, from petroleum. When we look at petroleum itself, liquid petroleum or oil, there's not a whole lot of aromatics. This is our source mostly for alkanes, some alkenes, smaller molecules. But when we start talking about coal, we can use coal, heat it to an insane temperature here, to produce a material called coke. Coke is incorporated into steel. It's a somewhat purified version of carbon. The coal tar, however, the remaining 30% of the material that comes out, contains multiple aromatic hydrocarbons. It's used in a whole bunch of different things for preparing these chemical feedstocks that we're talking about today. It is highly carcinogenic. And so many of the compounds that we'll talk about in this description of aromaticity, at least the small aromatic molecules, are particularly toxic. For a local touch here in Michigan, we have a number of different oil refining plants. This is one taken of the Marathon oil plant, sort of downriver Detroit. And these tall structures here are the coking towers where that coking would take place. Some examples here of aromatic hydrocarbons that we would find in coal tar include benzene, boiling point around 80 degrees. We see toluene here, which is the common name for a methylbenzene. We see xylene, which is the common name for a dimethylbenzene. It should stand to reason that there are 3 different versions of xylene. There's the so-called orthoxylene, where the 2 substituents are at carbons 1 and 2. Metaxylene, which meta is going to refer to a 1,3 orientation. And paraxylene, that para nomenclature is equivalent to saying 1,4. Quite often you'll see xylene used in the lab coming out of a bottle that just says xylenes, because they all have very similar properties to one another. You can see here the boiling points of all 3 are very close, and frankly, it's relatively difficult to separate them. So for sort of normal use as a solvent, you'll often see xylenes just as a mixture. We see some other ones here. Very common is naphthalene. We see this. This is the common ingredient in mothballs. So if you ever smelled that in a clothing store or something, biphenyl is a common one that you'll see sometimes in industry. And then some of these multiple aromatic rings, or these sort of so-called polycyclic aromatic hydrocarbons. You should be familiar with some of these names because even though we do have systematic naming, we could certainly call this molecule hydroxybenzene, or we could call this one methylbenzene or aminobenzene. These common names are so ingrained in chemical history that you will not escape them. So you should know the ones on this slide. These are going to be really commonly used in homework questions, commonly used in the lab and literature and things like that you will see. So toluene, again, methylbenzene. Phenol, we will talk about phenol again when we talk about alcohols, but phenol here is hydroxybenzene. Aniline, common name for aminobenzene. We get acetophenone. Remember that acete refers to a 2-carbon molecule. Phene here, we'll see in a moment, is sort of representing this phenyl ring, the benzene ring as a substituent. And ONE here meaning that we have a ketone. So we have a 2-carbon aromatic ring ketone. Benzaldehyde, so the aldehyde made from benzene. Benzoic acid, very, very common in industry for lots of things. The 3 different xylenes, this one being orthoxylene or 1,2-dimethylbenzene. And then styrene here, which is a common monomer in the production of polystyrene in plastics, styrofoam industry. So this is an alkene with a benzene ring as a substituent. Now, of course, there is a systematic way to name these. The IUPAC uses benzene as the parent name, and numbering is just like we've seen for other molecules. So in the instance where we have only one group attached, we don't have to number. We would just say bromobenzene or nitrobenzene or propylbenzene or whatever the substituent might be. If we have more than one group attached, we would name the molecule based on numbering we've learned for other cyclic molecules. So giving the 2 substituents the lowest possible combination of numbers. So one will always be a 1, the other one the lowest possible numbering scheme from there. If we have a long open chain part of the molecule, the rule sort of says that we would compare the size of the aromatic portion, 6 carbons, compared to the size of the open chain, whatever the parent chain would be for the open chain part of the molecule. And whichever one is longer, we would use that as the parent. So on the left, we have a 3-carbon piece attached to a 6-carbon ring. And so this would be a propyl group on a benzene ring, propylbenzene. On the right, we have a 7-carbon straight chain molecule with a 6-carbon ring attached to it somewhere. So since 7 carbons is bigger than 6, we would call this a heptane with something attached. Now when the benzene ring is used as an attachment, we use the attachment, the group name phenyl. So don't get confused here. We can have the phenyl group, which is the ring itself. We can also have a benzyl group, but that is the ring plus an extra CH2 group. So don't get confused here. If you see a benzyl group in a name, that means you have a ring plus an additional CH2 making that linkage. As I mentioned, if we have 2 substitutions, we can certainly number them. 1, 2, 1, 3, 1, 4 would be our options here. If we have more than 2 substituents, we do have to use numbers. However, if we have only 2, there's a specific naming system that can be used using these prefixes. So groups that are in the relative 1, 2 positioning to one another would be considered ortho. And so we could have a name down here, either 1, 2 dichlorobenzene, that would be appropriate, or ortho dichlorobenzene. Substituents at the 1 and 3 positions can be numbered 1, 3, or can be called meta. And again, at 1, 4, we can say para. So notice the naming here. We have the same sorts of prefix here, dichloro in this case, or dimethyl in this case. If we had 2 different substituents, we could still use the ortho or meta or para naming. We would just alphabetize these substituents. So we could do that, something like meta-chloromethylbenzene would be fine if we had a chlorine and a methyl group at 1, 3 positioning. In the instance where one of the groups makes our benzene into one of those parent molecules that you saw in the blue table a few slides ago, that becomes the parent chain. And so in this case, benzaldehyde is our parent. The carbon to which the aldehyde group is attached automatically becomes number 1, and everything else is referenced to that. So this would be 4-chlorobenzaldehyde or para-chlorobenzaldehyde. The benzaldehyde part tells us that this is carbon 1. And as I mentioned in passing, if we have multiple substituents, so more than 2, we have to number them all. So on the left here, we have 3 substituents. We number those so that we get the lowest set of numbers. And so that would be starting at this bottom right corner and going up and around to the left. That gives us a 1, a 2, and a 4 numbering. It doesn't matter what the things are, remember, just like in the case of cycloalkanes, we're getting the lowest set of numbers. So here we have 1, 2, and 4, and then we arrange the name so that they are alphabetical. So bromo before methyl. In the middle example, we have a parent that is one of those common names. So hydroxybenzene was called phenol. And so we have our parent chain shown in black here, including the OH group. That automatically, calling it a phenol, dictates the top carbon here to be number 1. That's the one attached to the OH group. And so then we number relative to that. We get the lowest numbering if we number around to the right. So we get a 2 and a 5 position for these methyl groups. So 2,5 dimethyl phenol. The one on the right is something that we're sort of familiar with from cartoons and TV, TNT, this explosive molecule. Toluene is the parent name for methylbenzene. And so calling this a toluene gives us our methyl group at position 1, and then our 3 nitro groups positioned relative to that at 2, 4, and 6. Notice it doesn't matter here if we numbered around clockwise or counterclockwise, it would still be 2, 4, and 6. And so we can go and we can look at examples like this, tell whether things are ortho, meta, or para disubstituted. We could go on to name those, and I'm going to skip these names, but you can certainly practice those. Likewise, problems like this give IUPAC names. In many cases, we will just have substituents attached to the parent chain of benzene. In some cases, we will have a different parent chain, in this case toluene, with some substituents attached to it. So look back at that blue table a few slides ago to note which ones of these you'll want to use as the parent chain. And again, we will skip these names. You can work through those on your own. Going in the reverse direction, drawing structures to correspond to names. Again, some will have benzene as the parent. Some will have one of the common names, aniline or toluene here. Some will use numbering, and some will use the ortho, meta, and para prefixes. Notice technically here, ortho, meta, and para, or the letters O, M, or P, are italicized. Of course, when you're writing these, it's hard to sort of italicize, but just be aware that's all it is the prefix. All right, so why do we care about aromatic molecules? Besides the fact that they're so common in nature, they are especially stable. So it turns out, and we could sort of prove this if we went back to our discussions from conjugation, when we look at molecular orbitals. We'll see one of those diagrams here in just a moment. It turns out that having one alkene bond in a ring distorts the geometry a little bit here, right? These two carbons should be sp2 hybridized as part of an alkene, but they're sort of stuck in this hexagon shape, which does not really accommodate the 120-degree angles that are necessary for sp2. That costs us a little bit of energy. And so the cyclohexene molecule is a little bit strained relative to the cyclohexane molecule, mostly that angle strain. When we put in two double bonds, particularly here in the case of having a conjugated diene, we see that that energy level goes up by not quite double, from 118 to 230. A little bit of that savings is due to the conjugation, but still we have a relatively more reactive, a relatively strained molecule here. We would then predict that something with 3 double bonds should be roughly 3 times, or about 350 kilojoules per mole. But in fact, that aromaticity that we have, the fact that we can draw the resonance structures where these extra electrons can delocalize all the way around all 6 carbons here, it actually saves us about 150 kilojoules per mole, such that a benzene ring is actually, right here, more stable than a conjugated diene, or a hexadiene, I guess I should say, conjugated hexadiene. We're going to see this in the chapter on aromatic reactions, that the driving force in sort of doing some of the reactions we're going to talk about is restoring this aromatic system, this extra stable aromatic system. And so what does this mean in practical terms? Well, what it means is that while we can very easily react a standalone alkene with any number of reagents to get an addition product, we saw a bunch of these types of reactions at the bottom in the alkenes chapter. We saw more recently in the conjugation chapter that we can react a conjugated diene with a number of reactants and get similar products to that. But we saw that there was a little bit of delocalization and that we could get a 1,2 or a 1,4 addition product in the case of the conjugated diene. Well, it turns out that if we do benzene reacting with bromine all by itself, nothing happens. We need a catalyst to drive this. We're going to see this kind of a pattern in the next chapter, in that benzene rings don't undergo addition reactions like we've seen for alkenes and dienes. They actually undergo substitution reactions, whereby we replace one of the aromatic hydrogens with whatever group it is we're adding, in this case a bromine atom. We do not form an addition product, because notice that forming this addition product would then leave us with a conjugated diene. We're actually going up in energy, right? We're going from that extra stable aromatic ring to a less stable conjugated diene. And generally speaking, favorable reactions don't increase the energy of the molecule. So as we will see in the next chapter, the mechanism for this involves temporarily breaking the aromatic system by using these pi electrons to do some work, but then we restore the pi electrons into this aromatic system. We restore that stability. So these are all substitution reactions, and we'll spend a chapter on those coming up soon. How do we know that these molecules are extra stable? Well, remember that we can measure bond length. Microscopy allows us now to measure bond length, and what we know is that single bonds ought to be about 150 picometers long. Double bonds are closer to 130 picometers. The bond lengths of benzenes are in between, right around 140. And what that indicates to us is that there is resonance here, that these electrons are not focused as shown here, top left, bottom left, and right, or top right, bottom right, and left. They're actually delocalized, separated by resonance here. So we can imagine these electrons being spread amongst all 6 carbons. It's very easy to see that if we go back and revisit molecular orbital theory. Those 6 pi electrons shown in as the overlap of 6 atomic p orbitals, those extra orbitals left over from sp2 hybridization of our 6 carbons. Remember from before when we talked about conjugation, the number of atomic orbitals that go into an MO diagram indicate the number of molecular orbitals that we'll have sort of on the molecular side. Half of those will be lower in energy, the so-called bonding orbitals, and half will be higher in energy, the so-called anti-bonding orbitals. And as we might remember from before, there are different arrangements of our p orbitals that we could think of, giving rise to these different energy levels. Since we have only 6 electrons in here, we can easily fill in those electrons into these bonding orbitals, and we have no electrons in the anti-bonding orbitals. This gives us a particularly stable system of 6 carbon atoms with 6 pi electrons. This concept was formalized in the 1930s, and forgive my mispronunciation if that's so. I've heard this pronounced a couple ways. I call this Huckel's rule. I've heard Huckel's rule as well. But in 1931, this was conceptualized into a rule, saying that aromaticity has a few components to it. The molecule has to be planar or very near planar. This allows those p orbitals to overlap one another so that electrons can flow between them. Of course, in the case of benzene, we have sp2 hybridized carbons all the way around, so this is perfectly flat. It has to be cyclical, of course. We have to be able to move electrons around and around and around. And it has to have the right number of electrons to satisfy that MO diagram. So the rule says the number of pi electrons needs to be 4n plus 2. Now be careful here. N does not mean the number of carbons. N is just an integer. So we can have an aromatic molecule with 6 pi electrons, like benzene. That would be for an N of 1. We could also have an aromatic molecule with 10 or 14 or 18 pi electrons for Ns of 2 or 3 or 4 and so on. So what happens if we don't have that number? Well, if we don't have that number, we have 2 choices, and the language here is tough. I apologize. Molecules that just don't have the right number of electrons would just be not aromatic. We would just say they're not, they're something else. However, planar molecules that are in fact conjugated, and so we've got a couple of those criteria satisfied here, but if they specifically have 4n pi electrons, not 4n plus 2, 4n, these are considered anti-aromatic. One example here is cyclobutadiene, which looks like this. Now, hopefully, you can look at this and say that's a pretty strained molecule. It's a square to begin with, so that's got some pretty significant angle strain. We also now are forcing in these double bonds, which additional angle strain. This has been made, however, it's very unstable, and it can undergo a Diels-Alder reaction with itself, even at dry ice temperatures. So we can have 3 molecules reacting together. Diels-Alder, here's your diene, and here would be your dienophile. And we could react once on one side, once on the other side to get this 3-ringed molecule over here, which itself is not particularly stable. We can also have larger ones. Cyclooctatetraene is an example. Now we've got 8 carbons with 8 pi electrons. Notice here we do have that cyclic requirement met. We also have the conjugated system that looks right here. However, when we start to look at the actual 3-dimensional shape of this thing, it actually contorts a bit. So you can go back to your discussions from Organic 1 about cyclohexane molecules and how a cyclohexane is not flat, even though we draw it flat, that it puckers a bit. And we talked then about boat and chair conformations. This is the same kind of logic here, that forming this into a boat-like conformation, we don't call it a boat here, but a boat-like conformation reduces some of the strain of that angle and steric and torsional strain that we would talk about for this molecule. When we go in and we measure the distances of this thing, we see that the CC bond distances are identical. Now, in fact, this molecule has been made. It was made in Germany in 1905, and here's the synthetic scheme. It doesn't matter, but we ended up with this molecule. It was confirmed later on, made it in a different way, and this one I think is one of my favorite syntheses, that we take this super high energy 2-carbon molecule, this acetylene or ethine, and we react it with some pretty wicked stuff here, and a lot of heat and a lot of pressure, and poof, we get this molecule. However, it forms explosive peroxides. It's really unstable. We can show why if we look at an MO diagram for this molecule. And so we can start to show that those electrons are in fact not where they need to be. The rule has to change a little bit for three-dimensional molecules. And of course, I know all molecules are three-dimensional, but I think you know what I mean here. These are molecules that have significant three-dimensionality to them. So the so-called fullerenes, Buckminster fullerene is the original one, which is shown here. Kind of looks like a soccer ball with alternating sort of molecular panels of 5- and 6-membered rings. Aromatic 3D molecules have a modified rule. Instead of 4n plus 2, the rule says it is 2 quantity n plus 1 squared. That would give us an aromatic molecule. If we were to draw out this molecule and we were to go in and count up all of the pi electrons, we've got 60 of them. 60 does not fit this pattern, therefore it is not aromatic. There are other versions of three-dimensional molecules that have been made that are aromatic. We don't, of course, have to have all neutral molecules. We can have ions that fulfill our core requirements. So I'm going to take a minute to look at this diagram. Just focus on the top for me for a minute. If we look at a 5-carbon molecule here, 1,3-cyclopentadiene, hopefully you can see that this would not be aromatic. It is conjugated. It is a diene here. But it's not conjugated because we have an sp3 hybridized carbon at the top point. That would disrupt the overlap of the p orbitals going all the way around the molecule. We can do several things to this. We could imagine taking off a hydride ion, so an H with its electrons, to get this first molecule, or ion, I guess. We could imagine taking off an H radical to get this radical molecule in the center. Or we could imagine just losing a proton, just the H part, leaving the electrons behind to get an anion. 3 different types of reactions we could do here. And I want to explore the outcome in each case. So in each of these 3 cases, we have an sp2 hybridized carbon in that top position. So in the case of the cation, we have an sp2 hybridized carbon. The p atomic orbital that's left over is empty. There's no electrons in it. So this cation is cyclic. It is planar. It's sp2 hybridized all the way around, but it only has 4 pi electrons. So this would be an anti-aromatic kind of a case. The radical, sp2 hybridized, we now have 1 electron in that leftover p orbital. So it has 5 pi electrons. This is not the 4n anti-aromatic case, nor is it the 4n plus 2 aromatic case. This is something else. This is just not aromatic. However, the anion, where we've left behind a pair of electrons in that unused p orbital, now we have a cyclic flat molecule, and we have a total of 6 pi electrons. 2 double bonds here, 2 and 4 electrons total, and then 2 more electrons in that empty p orbital. So 6 pi electrons. This anion is aromatic. If we look at a different example now, a 7-carbon molecule, which admittedly looks a little bit odd. We're not used to drawing 7s necessarily. We can see that same sp3 hybridization on the top carbon. This sort of blocks our potential to be aromatic. We do have this 3-bond conjugated system down below, but we're not aromatic. Again, we have the same 3 manipulations. We could lose a hydride ion to get this cation. We could lose a radical, or we could lose a proton. And you can see the electron counts at the bottoms. In this case, the cation is the aromatic one. We have 7 carbons here, all sp2 hybridized, cyclic, planar, and we now only have 6 pi electrons. And so we end up with an aromatic molecule. You could draw resonance structures here that would move these double bonds around the ring. So the point of this slide is to say it doesn't just have to be neutral molecules. There are cases where an anion would be aromatic, and there are cases where a cation would be aromatic. So who cares about this? Well, because we're able to form this stable anion, the pKa of this proton is much, much lower. Or that is, this molecule is much more acidic than we would predict for a plain old alkane. We're able to remove this hydrogen very easily because we end up with a stable product. Likewise here, cycloheptatriene, this molecule, would be a very good hydride ion donor. Normally we think about hydride ion coming from a salt, like sodium hydride or something like that. But in this case, this molecule could be convinced pretty easily to give away a hydride ion because the product here would be very stable. It would not be very acidic because this product isn't stable, but it could give away a hydride ion to produce a stable aromatic, in this case, cation. We can do this as well with heterocyclic molecules. So it doesn't have to be all carbons playground here. Here are a couple of molecules, pyridine and pyrimidine. You probably have heard these words maybe in an intro biology class. But pyridine is a common lab solvent. It is a cyclic molecule. It is conjugated, and it has 4n plus 2 pi electrons. So if we look at this and we say, well, what's the hybridization on this nitrogen? It is 1, 2, 3 groups of electrons. And so we would say that is sp2 hybridized. So where are those extra electrons? Because if we count this up, we've got actually 8 sort of extra electrons in here. Which ones of them are in the aromatic system? Well, this gets a little tricky for people sometimes. So what we want to think about here, let me get my little pen turned on here. What we want to think about is what are the bonding electrons doing? So those electrons are in a hybrid orbital, and those electrons are in a hybrid orbital. And so the third sp2 hybrid position is the lone pair of electrons, as indicated here. Well, so what does that mean for us? Well, that means that our pi electrons are those here, and here, and here, pi electrons. So we're counting up 2, 4, 6 pi electrons. That's a Huckel number, 4n plus 2, right? That's a 6 electron system. That gives us an aromatic molecule. Well, what about the one at the bottom, pyrimidine? Exactly the same thing. I have 2 nitrogens now at positions 1 and 3. But again, those, so I should be consistent in my colors, pardon me. Those molecules, or sorry, those electrons, get rid of this for you. Those electrons are in here, the sp2 orbital. And these electrons on nitrogen 3 are in the sp2 orbital. And so our pi electrons now are just the 6 shown inside the ring. So that gives us our aromatic number here, 2, 4, 6 pi electrons. So these are 2 examples of aromatic heterocycles. Now, what else do we have going on? Let's look at these next couple of molecules, pyrrole and imidazole. Now, pyrrole, when we look at it, now you're going to say, well, wait a second, we're seemingly counting these nitrogen electrons. Well, why is that? Well, let's get our colors the same again. If we identify the hybridization on that nitrogen, it is again sp2 hybridized. This time the sp2 are these two single bonds and the single bond bonding to this hydrogen. Those are our sp2 hybrid orbitals. And so that leaves us with the lone pair of electrons that must be in that unused p orbital, if we're talking atomic stuff, or a pi orbital if we're talking molecular stuff. So here and here and here are the pi electrons. So 6 pi electrons in a flat cyclic ring, that gets us an aromatic designation. Likewise, if we look at the bottom molecule, now 2 nitrogens, but notice the nitrogens are in different contexts. This nitrogen that's participating in a double bond would have 1, 2, 3 groups of electrons that are sp2 hybrid. And while I'm on red, I'm going to highlight them for the bottom nitrogen. 1, 2, 3, sp2. And so our pi electrons now, for nitrogen number 3, our pi electrons are the double bond. Also, of course, the CC double bond would count. And now on nitrogen 1, that lone pair of electrons counts. It's because they're in different contexts, right? The nitrogen that was participating already in a double bond in the ring, that nitrogen's lone pair is in the sp2 orbital because it was part of a double bond that's occupying its extra p orbital. However, the nitrogen that was singly bonded 3 times, its lone pair is in a p orbital. So take a moment, pause the video here, look at imidazole and make sure that that makes sense, because you're going to be asked to identify which electrons are in which kind of an orbital. And imidazole is a really good example because it has both. It has the doubly bonded nitrogen with a lone pair that lone pair would not count towards aromaticity, and it has the singly bonded nitrogen that would count. Of course, we can look also at, just like we saw in the previous sort of example, what if we made imidazole into a cation or into an anion? So the cation format would have something bonded to this nitrogen up here. So it's shown as an R group. It could be a hydrogen as well. That is going to be a pK of about 14.5 to get rid of that R group there. It's a little bit elevated. Whereas the imidazolide anion, having the negative charge down here, this one now we're losing, we would be losing a hydrogen that's connected by an sp2 orbital. And so we can lose that one relatively easily. As we go through and we look at some examples of aromaticity in the world outside of this class, we can see those in terms of biology. Again, I mentioned you may have seen the word pyrimidine in biology. So cytosine, thymine, and uracil are so-called pyrimidine bases in DNA. And you can sort of see, hopefully, that pyrimidine skeleton, if you will, in the middle with those 2 nitrogens. We also see an aromatic ring in histidine, in the amino acid histidine here. So again, this looks an awful lot like the molecule we just saw on the previous slide. I mentioned off the top polycyclic aromatic compounds that don't necessarily fit with the rule that we described. These are a little bit harder to look at. Naphthalene does work here in that we have 10 pi electrons, and so that fits Huckel's rule. 2, 4, 6, 8, 10, 12, 14. Anthracene also works. These are both aromatics, and they're just grouped together as polycyclic aromatic hydrocarbons. Some of these larger ones here, anthracene isn't great for us. Benzoapyrene is a really potent carcinogen found in tobacco smoke and other places. We see coronine here, named for the sort of corona of the sun, sort of this super cycle, if you will. This has been used in superconducting nanotubes. So imagine this is a cross section of a nanotube. We have lots of overlapping electron spaces that we can move those electrons through very quickly. PAHs as a group behave quite a bit like monocyclic aromatics. We can draw resonance structures. Of course, we could draw a ton of resonance structures for something like naphthalene or anthracene. They also undergo substitution. So these conditions, bromine and an iron catalyst, are discussed in the next chapter, but these are the ones that we saw earlier today that would attach a bromine, do a substitution reaction to make bromobenzene. We can use the same kind of a process to make bromonaphthalene. Naphthalene is an aromatic, and if we look at its MO diagram, or at least a cartoon of its molecular orbital potential here, it is planar, being sp2 hybridized throughout. It's conjugated, of course, it's cyclic, and it has a Huckel number of electrons, 4n plus 2, so it is aromatic. We can sort of see how that overlap would work here. There are versions of these as well that replace carbon with a heteroatom. So just so you can see a couple of those, quinoline and isoquinoline, two different versions of a similar molecule. Indole is a very common organic precursor that you'll see here and there. And purine, which is sort of it is its own molecule, but it's also the namesake for the other DNA bases, adenine and guanine, the so-called purine bases. You can see that purine kind of core structure. We can see a bicyclic aromatic here in the amino acid tryptophan, now where we have a nitrogen there. And in quinine, which is an anti-malarial agent that is also found in tonic water, for instance. We can see this sort of naphthalene derivative here, as well as some other difficult to synthesize biological stuff. Last topic in chapter 15 talks about spectroscopy of aromatics, and this is a tough topic for me to sort of deal with here, and that's just because aromatic rings produce generally multiple peaks that are not particularly impressive. So what do I mean by that? The computer can distinguish the substitution pattern down in the fingerprint region. You likely will not be able to distinguish this by eye, but a computer analysis of an infrared spectrum can do that. For instance, if we look at, well, just a second. The aromatic ring itself, we're going to be talking about a weak peak just above where the alkanes show up. So the books say about 30-30 to 30-50 kind of a number. This is going to be the CH for the aromatic carbon going to a hydrogen, and medium peaks down in the lower region. And I'll show you an example here. So this is toluene or methylbenzene. A lot of stuff going on. So as we've talked about in IR, alkanes typically show up around 2900 as a collection of overlapping peaks. In this case, this would be predominantly due to the CH3 group on methylbenzene. And then we can see a pronounced peak here at 30-30. This is the aromatic CH. You won't always see this because it'll often be obscured by the alkane peaks. Likewise, the bonds of the ring themselves, the books mention 1500 and 1600 as sharp peaks. More often you'll hear talk of aromatic overtones in the sort of 18, 19, 2000 kind of range up here. These are really easy to overlook. So I like to think of these as more supportive evidence that there is an aromatic ring rather than sort of first line evidence. And then as mentioned down here, if the fingerprint region is clean enough and or if you have computer support, you can pick out the substitution pattern, in this case a monosubstituted ring. NMR is a little bit more useful because the aromatic ring has this cyclization of electrons. Maybe you recall from a physics class that when we have moving electrically charged particles, those generate their own little magnetic field. And so in NMR, of course, the M being magnet, that magnetic field is important. In effect, we're de-shielding the outer protons. We are also shielding a bit the inner protons. So sometimes inner protons, if we have a large enough molecule such that there are inner protons, those can end up actually in the negatives on an NMR scale. But our outer protons are de-shielded, and so we end up with those protons showing up. Most books say 6.5 to 8 is kind of the region. So if you see anything out here on an HNMR around that, nominally 7 kind of an area, that's probably an aromatic ring. And then because we can see the number of unique signals as well as the splitting, this is really helpful for us to distinguish the branching pattern on the ring, the substitution pattern. So seeing 2 doublets like this, that's going to indicate symmetry, so a pair substitution. One of these would be indicative of these 2 protons closer to the bromine, the other one indicative of those 2 protons closer to the methyl group in this case. And then here also we see, of course, the methyl protons that are not where methyls should normally be. They are themselves de-shielded based on being close to that aromatic ring. So proton NMR is super, super useful. Here is an example of one, although I have not been able to find a spectrum to show you, but the molecule 18-annuline, which looks like this, is aromatic, but large enough that some of the protons point to the inside of the ring structure. And what we see is that those outside protons are tremendously shifted up above 9, which is not typical for normal organic aromatic molecules. Usually 6.5 to 8, and this is particularly shifted. But then the inside ones actually show up at -3. This is one of the very few examples of something showing up on a negative, the negative part of the scale. Typically, our organic aromatics are going to show up in the 6.5 to 8 range. Okay, likewise, carbon NMR, same kind of idea. We have some de-shielding going on such that aromatic carbons are going to show up in the neighborhood of 110 to 140 kind of a range. So much higher than alkenes, right? Alkenes, we're typically going to be talking about showing up in a couple dozen kind of a range. Aromatics are going to be showing up considerably higher, up in that above 100 sort of a range, similar to alkenes. So since they're similar to alkenes, you can't use carbon NMR by itself. Typically, you'd be looking at proton NMR to really help out. IR would help out. But if you have access to a proton NMR, is the best for identifying these guys. I showed you a couple of examples earlier of pharmaceuticals and biological molecules. And this bit at the end is just to show another sort of reason that we should be interested in aromatic molecules. So when in sort of drug development, we find something that works. And in this case, I would argue that aspirin was found as a natural product a long time ago. People had been making teas, for instance, out of willow bark for a while. They knew that it reduced pain and swelling and all of that kind of stuff for a long time. We have a lot of molecules now that are sort of based on derivatives. So a lot of new drug development is either, frankly, quite random, making large libraries of molecules and testing a bunch of them, or modifying molecules that we know work for something. And so here's an example of some NSAID drugs as well as COX-1 and COX-2 inhibitors. So we have aspirin, we have ibuprofen here, naproxen, which is sold under a couple of brand names, including Aleve. We've got Celebrex and Vioxx as a couple other pharmaceuticals that have been developed in this line. And hopefully you can see some similarities between some pairs of these molecules. Of course, there are differences, but once we find a structure that nominally works, then it's very easy to imagine modifying that structure in some way to make it more bioavailable, or to reduce side effects, or to make it less expensive. In some cases, to prevent it from crossing maybe the blood-brain barrier. There are lots of really good examples of drug development that have taken a core from nature, a core structure from a natural product, and then exploited it, changed it, modified it, and tested it in different ways to see how we can make it better. And so the sort of baseline take home here is that a lot of different pharmaceuticals contain aromatic motifs. And so as we wrap this chapter up, important concepts. So the definition of aromaticity, how we identify it, being able to do those manipulations with compounds and ions, counting up pi electrons. So this would be in terms of identifying hybridization, looking at which electrons would count towards that 4n plus 2 target. To some extent, being able to explain a molecular orbital diagram and why this works. A little bit less so the polycyclic stuff, but just as an introduction. And then spec as a sort of underlying thread that helps us to do some of those problems and to identify some of the molecules that we might want to look at. So that is chapter 15 in a nutshell. And so for now, we'll call it a day. Thanks for listening.